Let's take some time now to use implicit differentiation to figure out the slopes along some inverse functions. And the four inverse functions I want to work with today are the natural log of x, which is the inverse of e to the x, the arctangent function, which is the inverse of tangent, the arcsine function, which is the inverse of sine, and then finally the arccosine function, which is the inverse of cosine. And I first want to explore their derivatives very graphically. What I want to do is move along the curve and estimate the slopes at various locations and plot them as y values. So when we look at the natural log function, it begins with very steep slopes, and then it moves along to slopes of about 1, and then those slopes flatten out even further, approaching slopes of 0. So if we were to plot those slopes as y values, it would look something like this. There, the slope is about 1, and then as we keep going, the slope seems to be getting closer and closer to 0. And perhaps you recognize that curve, and we'll derive that curve's equation or function in a few minutes. We can do the same thing with the arctangent function. It begins very flat, and then it approaches a slope of 1, and then it gets very flat again. So if we were to plot those slopes as y values, it might look something like this. Approaching a slope of 1, and then approaching slopes of 0 again. And then for the arcsine function, it's only defined between -1 and 1, so it has a very small interval in which you can see its graph. But it begins with very steep slopes, approaches a slope of 1, and then it gets very steep again. So if we were to plot those slopes as y values, it might look something like this. Sort of a U shape. And then finally, the arccosine function is also defined between -1 and 1. But its slopes are always negative, and we start very negative, and then we get to a slope of about -1, and then we get very negative again. So that would look something like this if we were to plot those slopes as y values. And sort of a U shape, again, that opens down as opposed to the arcsine's derivative graph, which opens up. So even without knowing the actual functions or the derivatives of these functions, we can still visualize what they might look like. And now let's see if we can attack it more analytically. So I'm going to do all four of them at the same time, just across the bottom here. Then we'll practice using them in a few minutes. And what we're going to do is we're going to rewrite each equation using its inverse function, whose derivative we do know. For example, y equals the natural log of x, we're going to rewrite as e to the y equals x, because we know how to differentiate e to the y. And then we're going to take the derivative implicitly, and what that means is that we're going to get a dy dx or a d theta dx anytime we differentiate y or theta. And then finally, we're going to solve for dy dx. All right, so let's do the first one. Let's do y equals the natural log of x. So what I'm going to do is rewrite this as e to the y equals x, and now take the derivative implicitly. And the derivative of e to the y is e to the y times dy dx. That's the chain rule. Equals, and the derivative of x is 1. And that means that dy dx is 1 over e to the y. But I want my answer in terms of x's. So I'm going to look at that e to the y and say, oh, that's the same thing as x. So dy dx is 1 over x. And that is the derivative of the natural log function. And it's the function that models all those points that we plotted there, all those slopes that we plotted as y values. Let's move on to the arctangent function. So now we're going to work with theta equals the arctangent of x. Just like before on the previous example, we're going to rewrite this function. So now rewrite this equation. So now the tangent of theta equals x. And now we're going to differentiate implicitly. And the derivative of tangent is secant squared theta. The chain rule requires us to multiply by d theta dx. And the derivative on the right-hand side is 1. So d theta dx is 1 over secant squared theta, which I'm going to write as cosine squared theta. And just like before, we want our answer in terms of x. So I'm going to draw a little picture now of a right triangle with that theta in one of the acute angles. And if the tangent of theta is x, this equation right here, that means that x has to be opposite and 1 has to be adjacent, so that the tangent of theta is indeed x. And that makes the hypotenuse 1 plus x squared. So our cosine squared then is going to be 1 over the square root of 1 plus x squared, all being squared. Cosine is adjacent over hypotenuse. And that simplifies to 1 over 1 plus x squared. And that's the derivative of arctangent. And if we were to graph this on our calculator, we would get a curve that's very flat, comes up and hits 1 when x is 0, and then gets very flat again. Now perhaps you can do the next two yourself, or stay a little bit ahead of me as you're writing. So you could either do that or you could pause the video, but I'll go ahead and work it here. And we're now going to look at theta equals the arcsine of x. I'm going to rewrite the equation as the sine of theta equals x. And then I'm going to take the derivative implicitly. So the derivative of sine is cosine. The chain rule says multiply by d theta dx. The derivative on the right is 1. So d theta dx is 1 over the cosine of theta. Again, I want that answer in terms of x and not theta. So I'm going to draw a right triangle. And using this equation, x must be opposite, and 1 must be the hypotenuse, which makes that third side, using the Pythagorean theorem, the square root of 1 minus x squared. And now I can write 1 over the cosine. And the cosine is just adjacent over hypotenuse. So I'm going to get 1 over the square root of 1 minus x squared. And that is the equation of the curve that these dots are mapping out on the graph. And then finally, we'll do theta equals arccosine of x. So just like before, we're going to rewrite this equation. We're going to take the derivative of the equation. Again, the chain rule requires d theta dx, and then 1 on the right-hand side. So d theta dx is equal to negative 1 over the sine of theta. And this triangle, I'll draw it up here since I don't have a lot of space down below. If I put theta here, this equation tells me that x is adjacent and 1 is the hypotenuse. So the opposite side is 1 minus x squared, all inside the square root. So d theta dx is equal to negative 1 over the sine of theta here is just going to be the opposite over 1, so just the opposite side. And I get negative 1 minus x squared inside the square root. And that equation models these dots as a function. So those are the derivations of the 4 different inverse trig functions we're going to use a lot this year. You don't have to remember the derivations, but I'm hoping the derivations give you a little bit of context for why these derivatives look the way they look. And on this next page, I show you my derivatives chart, which is what you'll see on the wall in my classroom. And what we have just done today is found the derivatives of the natural log function, the arcsine function, the arccosine function, and the arctangent function. The only one left to do is this one, which I hope to do in the next couple of weeks. So now that we know how to take derivatives of these inverse functions, let's practice using them. And I put in the right-hand column here ones that involve the arc trig functions. The ones on the left don't, so I'm just going to go ahead and focus on the ones on the right. So the derivative of arcsine of 7x. Well, we look up here, and the arcsine function, there's the structure of its derivative. Remember that x is a placeholder, so we have x there, so x shows up down below. Here we have 7x, so 7x is going to show up down below. So I'm going to get 1 over, whoops, let me just write dy dx. Oh, I guess it's already been written there. So let me just erase what I have here. And the derivative of arcsine of 7x is going to be 1 over the square root of 1 minus 7x squared times 7. And that's the chain rule. The derivative of the interior is 7x. And in a textbook, you might see that as 7 over the square root of 1 minus 49x squared. Here's another example that requires the product rule. And again, we're going to let u be our first factor and let v be our second factor. And the derivative of stuff to the second is 2 stuff to the first times the derivative of that stuff, which is 1 over 1 plus x squared. That's just u prime. And then I have to write v, and then plus u, which is the arctangent of x, all being squared, times v prime, which is 5e to the 5x. And let's do the third one. So here we have 3 factors, so we're going to have to use the product rule again. And as you know, when we take our derivative here, we're going to have 3 terms: u prime vw, then we're going to have u v prime w, and then we're going to have u v w prime. So here they all are. So here is u prime, and then there's v, and there's w, plus, and then here's u, and then here's v prime, and then there's w, plus, and then here's u, and then there's v, and then here comes w's derivative. 1 over 1 plus 16t squared, that's 4t all being squared, times the derivative of 4t, which is 4. All right, I hope that made some sense. Let's now look at the last 4 items here. In the first one, what I want you to see here, actually in this first pair, is that you can often simplify functions before you take their derivatives. So look at this expression, the ln of x to the 5th. If we treat this function just as it is, the ln of stuff, the derivative of that is going to be 1 over the stuff times the derivative of the stuff. And that cleans up to be 5 over x. But we could have, before taking the derivative, move this exponent of 5, which is inside the natural log argument, and put it out in front. And if we put it out in front, and that's using a pre-calculus property of natural log, or all logs, then if you rewrite it this way, then you can just carry along the 5, take the derivative of the natural log, which is 1 over x, and you get a result that's equivalent. So either approach works. Sometimes adjusting your function before you take its derivative can be helpful. And then here are 2 more examples. Looking at this expression here, e to the natural log of x, well, we know that e and the natural log undo each other. So this is really nothing more than taking the derivative of x, and the derivative of x is 1. And then in this example, we're taking the derivative of e to the 4 ln x. We want to cancel out the e and the ln because they undo each other, but the 4 is in the way. But we can move the 4 back into the natural log expression. So we can think of this as the derivative of e to the ln of x to the 4th. And now the e and the ln cancel out, and we're taking the derivative of x to the 4th, which is 4x cubed. And that's it.